Hello, guys. My name is Gavin Smaragia. I'm a CTO at Afribot, and I am the lead in the design stage. And I'll be taking you guys through this course, PCB Design. It's a 10-day program about PCB design. Basically, wanted to know about the level skill of everyone, put you guys into one cohort so that the content that we deliver to you guys is tailor-made and it's suitable for everyone. So I hope you're going to have a nice and looking forward to working with you guys for the next 10 days. I guess there's someone who's joined us. Please, you can give us a brief intro. There's someone. There's a Mr. Star. Please give us a brief intro of what you are, who you are, and what you do.
Hello. Hello. You guys hear me?
Yes.
My name is Jimhua. I work with a food delivery company called Dollout.
Okay, awesome. So without further ado, I think we can begin on this, unless there's someone with a comment before we start. Do we have such? Awesome. There is none. So let us begin. So, brief history about me. I'm Gans. I am the CTO at Afribots. We basically design and do consultation services for clients, and this involves ideation. Okay, mostly our clients usually come to us with ideas, and we are mainly involved in actualization of the idea. So that includes the PCB design and firmware design and things like that, and the software aspect of things, and knitting everything together to have a final product. So in this apprenticeship program, for the next 10 days, we'll be going through PCB design alone. And we can have a brief intro on what PCB design is, what is a PCB, why do we need to learn this, and how can it help us, and basically the softwares that you can use, and the various methods that are available in the current market for PCB designing, and why we need to know that. Yeah, so without further ado, and if there are no questions, I'll just begin. And as you can see, there's a couple of mambo jumbo on your screens. So this is what we call a circuit. Yeah. So this is a couple of resistors, transistors, capacitors, diodes, and everything put together in order to achieve a create your schematics. Almost everyone understands what a schematic is. Once you create a schematic and you will need to arrange it in such a manner that is safe, and not only safe, but that is also mechanically rigid, and everything connects together in a manner that it can easily be traced in case of any faults, and you can easily make it in such a way that it's also presentable as well. So why do we need PCB design? First of all, PCB stands for printed circuit board. This is a board or card that electrically connects and mechanically supports electrical components. Why do we need this? We need this for rigidity, as I said earlier, and also to maintain safety. These connections, the connections that are used to connect the components on the PCB are made usually with a series of conductive tracks and traces, which is usually copper that is laminated onto or in between sheets of non-conductive material. As I'll be going through the slides, we'll begin to see that. And I just wanted to show you why we need the PCB. So this is what we have without a PCB, and therefore, in order to achieve some level of neatness and security and safety, we need to have a sort of a system that is able to maintain and hold these components in a more professional manner. So this was how PCB design was done in the 50s. Basically, PCB design in the 50s was done via cables, the cables that connected through poles, and they were just tied via screws and nuts. There was no soldering. I hope everyone here understands what I mean by solder, but if you don't, we'll just go through it in the introduction bit. So there was no soldering. It was just you have your component, you have a couple of wires. For example, here, I hope you can see my mouse pointer. You can see there's a bridge between two poles, and there's a resistor, and then there's a wire that is coming out of that resistor going bridge on certain poles. So basically, in the 1950s, all connected. This not only made it bulky, but it made it in such a way that you can't really troubleshoot easily unless you're the one who built the system. For example, if you can see here, all these wires, all these cables, they are like hundreds of cables. If there's a fault on one area, it will take you days, and you have to be like really good at what you're doing to figure out where the fault is. So because of that, we needed a way to laminate this and shrink it further, because imagine with the thousands or millions of connections even. if every connection was basically tied over all, yeah, could be possible. So with this technology in the 1950s, in the 1960s and 70s came a new type of technology. So it was basically brought about by etching onto an unconductible etching on top of etching a copper piece on top of an unconductible substance. So you had a board. The board, for example, as you can see the brown part here, there's a board that is usually non-conductive, and then the engineers would draw using a pen on top of a layer of copper that is on top of the board. So the engineers will physically draw using a pen, and it's some interesting artwork if you want to search that later. So they used to draw using a pen on how the connections were supposed to go, and then the pen's ink used to not react to the substance that etches the copper. So you have a board with copper, you draw on top of it, and then you put it inside a chemical that will basically eat away all the other parts. So all these other parts that are not bright are sort of eaten away. And where the pen drew, you have these beautiful traces. These are the traces that I had said earlier, usually made of copper, and they're the ones that connect all these components. Yeah, they're the ones that connect all of these components. So from this in the 1950s to the 1960s and 70s, we came to this. You can see this here is a jump. It's basically when you made an error and you need to correct it after production has been made. So you need a wire like this. But you see, this wasn't sustainable. First of all, this could not be produced in a mass kind of manner. If you wanted to produce a lot of PCBs, you'll need a lot of people to begin drawing. Also, it wasn't really effective, especially if you had a lot of connections. So there in the late 80s, okay, still up to here, the main technology that was used was through-hole technology. Through-hole technology is some type of technology whereby we have components with legs. They have extra pins, and pins could be put into a hole drilled on the board that as we have spoken, and then solder used to fill it. We still have through-hole components up to now, but in the late 80s, the advent of computerization, whereby we saw companies like Casio introducing the calculator and the Casio watches, and I know everyone here knows at least some of that. So everyone sort of began checking out this new technology called surface mount technology in the late 80s. In the late 80s, so surface mount technology has the component with a bunch of legs or pins or whatever you might want to call this. And these pins will be connected onto just a pad of conductible surface that will have a solder on it. The solder will then act as a glue to attach the component that you need onto the board. So with this kind of technology, we were able to compress most of these materials. we were able to compress most of these materials, most of these components. Remember, we started we started with such kind of landscape in the late 50s and 1950s and early 60s. So rather than having your components all the way mambo jumbo like what we have here on screen, surface mount technology was able to reduce everything and basically shrink to what we have currently at the moment. So what we have at the moment is still an extension of surface mount technology, except the technology has been made better over the years in order to be able to fit into like very really tiny gadgets like smartwatches, mobile phones, and computer motherboards. So yeah, what do we have here? Here we have something we call a hobbyist playground. Yeah, so I think most of you guys here are hobbyists, and some of you might have made a couple of circuits here and there, and this is what I can expect from most of us. I know I've done this a couple of times. It works, it's fast, and yeah, for prototyping, it's usually not bad, I can say. It's not bad, I can say. So with this, we have a couple of wires everywhere. The kind of boards that are here can easily buy this at local shops or radio hacks and shops like electrical installation shops for around it's cheap, around $1 or half a dollar. But there's a more professional way of this in terms of mass production. If a company approaches you as a maker, I hope everyone here is a maker. If a company approaches you as a maker to say, contract you to develop a PCB for them, to develop components, and you have like 200 components that you have to attach together, and then you have to do 50 pieces of that. So how are you going to develop everything as we have mentioned here? And first of all, using such a fashion will take you ages really to complete. It will take you a lot of time to get done, and it will also make your work look unprofitable. So this is why we need PCB design. Yeah. So here, as you can see, this is an example of a modern PCB. Sorry for that. So this here is a modern PCB. As you can see, we have a couple of components. There's usually a mixture of components in whatever it is that you want to do. As you can see here, this is an SMT component. It's a microcontroller chip, as you can see from the label. I hope it's clear to everyone. And so on your software, once you create what it is that we want to do, once you create our PCB on software, we'll have such an output here, as you can see on the left side of your screens. So using this output, we can be able to produce this, manufacture this, even in a mass kind of way, in order to achieve such a production. So we go from here, your normal hobbyists and the things you create, to what we have here. So with this, we can easily send this out to a lot of manufacturers, and the manufacturers basically can be able to stitch everything together. And there are also a couple of ways that you yourself as an individual can get certain components like etchant, which is a chemical thing. You can get like a PCB with copper on top of the board. Not really a PCB, but you can get a board with copper clad, and then using the etchant, you can be able to print on a piece of paper, and basically your board to look in such a fashion. So that is still a PCB design. That is still a PCB, but as you can see, it's going to be really difficult for you to maintain things like tolerances if you're going to do it by hand. I know there's a couple of techniques that you can do. We can even cover a few, like just on a top level, in order to deeply understand this, but this can be done later. But there are a couple of ways which, once you create your PCB software, you can be able to transfer that onto a piece of copper cladding. So enough with the history, and I really want us to now begin speaking about how a PCB works and what everything here is. As you can see, there are a couple of holes, there are a couple of things that are happening here and there. I want us to go deeper into this. Is there anyone with a question before we proceed? Okay, so there is no one with a question. Awesome. Hopefully, I think I can proceed without leaving anyone behind. So, what is a PCB? What is it that makes up a PCB? So, a PCB is usually a non-conductive layer that has a copper section on top or below or beneath it. So the non-conductive layer is usually referred to as a substrate, and the most common type of substrate is FR4. So you don't really have to know what FR4 fully stands for, but if you really want to, you can Google search it, and it's FR usually stands for flame retardant, and 4 it's more of a standard material type from what we've had since the big PCB design. But what we have currently is called FR, which is a substrate, and it's usually a material made out of flame retardant epoxy resin and the fiberglass components. So the fiberglass and epoxy is what makes the PCB be able to like withstand soldering. If you're going to attach component, you're going to need to solder it on the board, and so once you're soldering, you're going to heat the board on up to temperatures like you're going to heat the board to about 160, 200 degrees. It's usually between 180 degrees to 300 degrees, depending on the kind of components you are soldering and the kind of finish your PCB has. But if you're going to heat something using 180 degrees Celsius, centigrade for anyone who uses Fahrenheit here. So if you're going to use something going to heat the board around 180, 200 degrees Celsius, we're going to need the board to be really strong in order to withstand such heat. So we usually have a substrate made up of FR4, a copper layer that is going to connect the different components. And the good thing with such a material and such a design is you can easily attach more layers. You can easily sandwich everything up together in order to have what you call a multi-layered board. So there are a couple of instances where this is needed, but it's usually designed for dedicated to high-speed circuits and or small form factor PCB boards, small form factor boards that you need to pack a punch. So once you have your small form factor board that you need to have a lot of materials, a lot of components, and say you're creating something that is going to fit on top of a wrist, a human wrist, you're going to have to compress everything. That is when you need a multi-layered board because you need to have a couple of wires up, down, here and there, and this just keeps everything neat. And there are a couple of design considerations that we're going to go through, and such design considerations should help you be able to understand what you need and how you can be able to route all these traces in order to make your PCB work well and not break down or have any effects. So the good thing with what you're doing is for now, we should not worry about multiple layers. That's for later. Let us just concentrate on what constitutes the PCB. So once you have your non-conductive layer, your substrate, that is FR4, the flame-resistant material made of fiberglass and epoxy resin, copper on top and below, we're going to need to etch this. We had spoken something small about etching, but etching basically involves, and I quote unquote, eating away some of this copper in order to have traces that run from one point to another. So this is just a cross-section view. But if you're going to have multiple components like what we see here, you're going to need some sections that are going to like act as a buffer between the first connection to another connection. So you're going to need like islands which have not yet been connected, and you're going to need parts that have been connected. So that is why you need to etch most of this copper in order to have exactly what you need and exactly the connections you want. So here we have an example of a plated through hole. A plated through hole involves drilling the PCB board, drilling what you have here, and then you now need to add copper onto the drilled hole in a process called electroplating. Yeah. So once you plate the hole, you're going to have a through hole, plated through hole pad, and with this you can be able to basically attach through hole components as seen, for example, with such components on top here. So we have holes like the ones I'm highlighting here, and with such holes, once you place the metallic pads on such components, you can solder it, and the plated through hole basically adds more rigidity to the material. Some of the boards that you can buy, the hobbyist boards that you can buy on local shops, they usually, some of them usually lack plated through holes. That is why most components that have been soldered on such kind of boards, I think they're usually called forgotten the name, but there's a name that people, not breadboards, I mean, there's a name that they usually call. I'll just attach that onto some documentation later on. But such PCB designs that lack such holes and you need to put through hole components in it are going to be less rigid, and the components usually fall off after a few weeks or months of motion. So you have been tasked to create a tracker for a company that really needs trackers on their fleets or a fleet management system, and you're doing the hardware PCB design. If you're not going to do very good plated through hole design, most of the components will fall off after a few runs of the vehicle through very rough terrain. So it's really important to keep that in mind. And then let's talk a bit about solder mask. So solder mask is what we can see here, the green part. So the green part is what covers the board. So if you have just a board with only copper, all the connections are made of copper with no covers on top of it. If say you're trying to attach your PCB onto your case, and your screwdriver falls on top of the PCB and the PCB is on, it can short all the connections. Since the screwdriver is usually conductive, made of conductive material, it can short most of the connections, most of the wiring connections. In order to avoid that, we need to add some sort of masking, some sort of interface between the copper layer and the environment. There are also other reasons that you might wish to have such or not wish to have such, but the solder mask is usually added on areas with which there's nothing attached, so there is no copper, or areas where there is copper, but you need to keep that insulated. And in areas where you need to attach a wire for soldering or test points for testing your PC, we're going to call the areas solder mask keep out. So these keep out areas are not really going to have any solder. So just a recap, we have our substrate, which is a flame resistant material, FR4, made of fiberglass and epoxy. We have copper. We have through hole components that are going to attach top and bottom components. If we have multiple layers, as we have seen here, we're going to have multiple vias and things like that. But for now, let us just focus on this. So we're going to have a solder mask keep out, where you will need to solder your components or attach wires or just have them open for whatever reason, they say for test points and things like that. And then on other areas, you're going to need to have the solder mask. Okay, so how is someone has asked a question. The good thing with what we're doing at the moment, if you're going to design a PCB on your computer, once you finish designing, you can there are a number of ways that you can keep these parameters. There are multiple ways that you can sort of force these parameters. So no, if you're going to create a solder mask, there's I'll just show you when we reach there, but there's a way in which using the software you can just draw a border. These are the regions that I want my solder mask to cover, or these are the regions that I do not want my solder mask to cover, and it can do that for you. Do you want to like specify or to like really have your design in such a manner that you want? But the good thing is mostly while you're focused, once you create your once you create your PCB, once you've routed your design, most of this solder masking and things like that is going to be done by software. So if you have a component that is going to be attached, the software itself, say KiCad or EasyEDA or whatever software that we're going to use, is going to automatically keep out the solder mask in areas where it needs to be kept out, unless you specifically wish the pads to be keep out areas. And if you're going to do this by your own, if you want to do the PCB design on your own, there are also a number of ways with which you can keep out this solder mask from certain areas. But we'll go through that later. So as you can see here, these are the kind of things that we have mentioned for the past few minutes. So here we have the green part, basically the whole green part, which is the solder mask. We have these parts that you can see like some golden-ish parts. These are the solder mask keep out areas that you're going to attach components and or going to pass through like test points or through holes. Going to have things like through holes. So then there's something, I don't know whether you've noticed, but most of these exposed pads are golden in color. So there's usually a surface finish that is made. It's called ENIG. ENIG. It stands for electroless nickel immersion gold, and this is important as it's going to ensure that the copper is not going to be eaten away. So if you've worked with copper components, or if you've worked with copper utensils or anything with copper, you will quickly notice that after some time, if you leave copper exposed, it's going to oxidize, it's going to turn color, and even making a connection, making joints, it's really difficult. So what is usually attached on top of the copper layers is the ENIG finish, what we call electroless nickel immersion gold, and it makes the pad have some goldish color. I don't know whether you can see that. It makes the pad have some goldish color. And with this goldish color, it's a very thin layer of gold. You can be sure that if you're going to attach your components, gold is one of the materials that is very hard and usually it oxidizes easy. So you're going to be sure that once you solder your components on top of your PCB, they're going to be really rigid and well attached. And that is what you really want, especially if you're going to do a professional PCB and or you're going to do an industrial PCB, not just a hobbyist thing. So yeah, we also have a silk screen layer, which is similar to the solder mask, except it's of the solder mask, and it's usually the color can be like white, blue, green, whatever it is that you want to write. And normally most people prefer white because white and green, because it gives the the look of a more professional PCB. But the silk screen layer is just a couple of writings, and it's usually done on top of the solder mask. So silk screen cannot be done on top of this surface finish, on top of the ENIG finishes, because on the ENIG finish, you need to attach most components, or you're going to need to solder through hole components and or surface mount components, and you really do not want to mess on top of that. You do not want to cover that on like any layer of impurities. Like if you add silk screen of such on top of the ENIG finish, it's going to make your components refuse to attach and or have a weak attach. So the good thing with most of these softwares like KiCad is KiCad offers a couple of design rule checks that once you finish designing a PCB, it can be able to run. You run the design rule check, and it can tell you if you can expect a failure on your PCB. So this is how the silk screen should look like. So it's just a couple of writings, and it's usually important, especially if you want to convey more information and or you want to achieve you want to achieve easier like debugging once you create your PCB. For most production PCBs, like if you open your computers, you check out the motherboards, most of them won't have a lot of markings unless where it's really necessary. For example, if you want to denote that if you're going to solder such an IC, this is where your IC should be, this is how your IC should be oriented. For example, as you can see, this C-shaped thing here, this U-shaped thing. So it's more of just to be able to outline and specifically show you the orientation and the outlook. But if you're going to create your first PCB, you can just have it in order for easier debugging once your PCB comes, because it might fail. It might have a couple of rogue connections here and there. So it's really not good or bad practice to have such, but it's really good practice to have a few information on the silk screen layer just to tell you about the orientations and just a few information like the version of the board. So you can have V1 here. You can also attach the name of your company or things like that. So yeah, up to this point, I guess we've covered mostly what this is. What do we have here? I think we've covered what we have, and from a more high level perspective, I guess most of us are now conversant with the technologies that have been used to create such a device, such a board, and everything that is involved on a high level basis. So is there any question before we proceed? Yeah. So if you have any question about what we have covered so far, beware that as we're going to process, going to have all topics on to do the design, the best practices for design. Like there are a lot of factors to consider for high-speed design, for critical design, and we're going to cover that later on. But up to this point, do we have anyone with a question on this? Awesome. So I guess that is a no. So I hope that up to this point, you are now can check out this. This here is an SMT component. This here is a through-hole component. This here plated through holes. This here like solder mask. We have connections running here made of copper with enig finish and things like that. So with this high level understanding, I guess it's now important for us to delve deeper into PCB design. Awesome. So yeah. So now that you know what a PCB is, it is important for us to understand these 8 or 9 steps of how we're going to create our own. So the first thing that we need to know is circuit design. So in this process, in this procedure, we had said we're going to use KiCad, and I personally prefer a mixture of KiCad and any other software that can be for PCB design. We have a lot. KiCad, I prefer KiCad because it's open source and it's free for anyone. And yeah, I don't know whether most of you have KiCad installed on your computers and or machines or laptops, but we're going to cover how we're going to do that in a short while. But yeah, so we're going to cover PCB design. We have a couple of softwares, as I've said, KiCad, we have Eagle, we have EasyEDA, we have Altium Designer. There are a couple of softwares. In fact, there are a lot of softwares, but we're going to cover mostly KiCad, and I'll be supplementing us with EasyEDA, because with EasyEDA, you can easily be able to link with a manufacturer, that is JLC PCB, in order to get your PCB boards manufactured. So I'm not going to delve deep into circuit design, because I assume everyone here knows how to create a circuit, and everyone here is a kind of proficient in circuit design, even on a basic perspective, because I really do not want us to cover circuit design. That will just take a lot of time, but we're going to cover just the basics and the best practices in order to achieve a good PCB design. So since this is a PCB design thing, since this is a PCB design thing, we're going to cover most of our content, like 95% of our content is going to be on PCB design and not on circuit design. This will enable us to cover a lot of topics as regards to PCB design. So once you design your circuit, you create a schematic. With creating a schematic, this might involve, once you create a circuit, you're going to have components on your circuit. You're going to have, say, a 555 timer, an Atmega 3 controller, or an STM32F1 controller. Going to have a couple of transistors, maybe SMT transistors or through-hole transistor in there. So if you check the manufacturers of these websites or components, of these components, you're going to find schematic symbols. Basically, these are the symbols that are going to present every component that you're going to use in our design. If you're going to use, say, an Atmega 328 PU, the Atmega 328 PU usually has its own footprint. We're going to see what that entails, but we need to have a symbol that will represent that of the circuit, and we're going to see how we're going to create our own and or import an already existing one from multiple libraries. So the good thing with most of the components that we have is, if there is a seller that is, say like you want to buy the components from, if you search the components on Octopart, it's going to link you to a bunch of sellers. You have DigiKey, we have you can actually buy directly from companies like Texas Instruments. We have LCSE in China. So if you're going to buy components from LCSE, you're going to they're also going to offer you footprints and schematics for that component. So it's easier for you to use components that have all their footprints available and schematic symbols available. But if you're going to miss that, we're going to see how we're going to create our own and import them into our schematic, and how we're going to create footprint. So the footprints is like by footprint I mean this here, what we have here. So how is it going to sort of to look like on software, and how are you going to export this for it to be manufactured in such a manner that you're sure once you buy the components it can fit, and the fit is usually like up to a very, very, very small millimeter fit. So you need this to be really accurate. So you're going to see how you're going to create our own footprints, and how you're going to attach our own footprints to the boards, and use on the design stage, and later on how that is going to be manufactured. So you're also going to see how we're going to generate a netlist and what a netlist is in a KiCad. We're going to check out how we're going to make the board layout, how we're going to separate everything in order to have a final design. So here is the board layout. How we're going to do this in order to have an output of this, as well as we're also going to check how we're going to make our boards ready for production, how we're going to generate the GABA files, how we're going to have a 3D view of our PCB board before we send it over for manufacturing, how we can export that in order to make it by ourselves on our own, and or how we can also be able to easily share this with companies like JLC PCB or PCBWay and or Next PCB to manufacture the components. We're also going to see how we can generate a BOM. A BOM stands for a bill of materials. How are we going to generate the bill of materials in order to share it with a seller in order to buy every component that is required, and or share it with a manufacturer that can be able to buy the components for us and do the PCB assembly, if you want to outsource that, because sometimes it's usually good for you to outsource the design, to outsource like manufacturing, because it makes it easier for you as a maker to focus on design and improving the design, rather than focusing on manufacturing and everything. And finally, I'll also talk on how we can order the PCB boards that we have created. Okay, awesome. So up to here, I hope there's no questions, but if you have, just just raise your hand and you can ask, and or you can chat on the in-call messages. Just send a message with your question and you can be able to answer that. Awesome. So so if you go to Google and you search KiCad, you see this organization here, kicad.org, and if you click on downloads, you can easily select. If you click on downloads, you can easily select your operating system. So on a show of hands and or votes, please everyone, can you type on the in-call messages whether you have the software, the KiCad software installed? If yes, please type, or if no, please type. I'm going to give you a minute just to do that. Okay, awesome. So from the responses, I can see most of us do not have the software installed. No worries. This is just an introduction, but hopefully by tomorrow everyone should have that. So once you just Google KiCad, I'm sharing that on the in-call messages. You can just Google KiCad, and on that you can be able to click download. With that, you can be able to select the operating system that you want, or the one that you're using, Linux, Windows, Mac, anything, and then select the kind of version of your computer. So, and basically download it. I'd prefer you only what you're sure works. Do not download the nightly builds as much as they're usually the latest ones. The code base is usually under development, and they might have a the design. You'll notice there's a couple of different to use KiCad or to do PCB design. So you really do not need to be a professional on electronics and or know much, but it's important for you to know at least some basic for you to understand how the connections can be made. The good thing with PCB design, if you have a good schematic, and you can get schematics really easily. Like whatever it is that you want to create, I guarantee there are a lot of open source projects that they are all like they are focused on creating schematics. I'm not going to advise you to I can't advise you to Google search and copy paste anything, because once in a while I usually check out some of these circuits, and there are usually a few bad apples. So someone just creates a circuit, really doesn't work, but you just post the schematic online, and it usually causes it usually makes a lot of beginners wonder, like, what is really happening? I've created everything as seen, nothing is really working. So there are a couple of sites that you can follow, and or a couple of open source projects that you can follow in order to know a few bits of circuit design. But generally, I'll share a couple of links as well. I'll share a couple of links in order for like a couple of links for like trustworthy websites and or places, resources that can use to learn. But I won't advise you guys to just Google search and pick anything at random, because some of these are usually wrong. And also another important thing is you can also, once you create your circuit, before you decide to come up with a PCB design, it's important for you to share with someone. Like if you know, say, I am good with circuit design, or this is cohort 2. So if you've met another person in cohort 2 who is really good in circuit design and or trying, we can create a community around this. We already have a WhatsApp group. We can create a community around this, which we can share with each other the boards that we've created, and how we can be able to help each other troubleshoot each other's circuits and make them better. So Biak is asking whether we need any we need to have any what if you don't have any basic knowledge on circuit design? Okay, so for what you're going to do, since we're covering mostly PCB design, I'll just go through a few basic procedures of circuit design. I won't really delve that much into it, because if we do that, we're going to have really limited time on doing the main PCB design that we are supposed to do. But with the basic concepts that we're going to cover, that is going to be enough for you to understand and follow up on what you're going to be doing. Because with circuit design, it really doesn't require you to know much in order for you to start designing your own PCB. But there are a couple of things that you need to know, such as the proper procedures and how these components are supposed to be connected. The good thing with also creating a circuit, and the thing that makes this sort of worthwhile is if you're going to create something, for example, let me just take a few minutes to assume I'm going to design. Let me take a few minutes to assume we're going to design a lithium-ion charger. So if you're going to design a lithium-ion charger, the first thing I'll do is I'll check on I'll check on the kind of BMS chips that we have, and the kind of chips that we can be able to access online. So this entails just basic research. You can check trustworthy websites like Circuit Digest and or Texas Instruments. They usually have very good guides and ways in which you can be able to understand everything that is required. So first, before you create your circuit, do some research on what it is you want to do. More research. Even if you are pretty sure that you have dealt with such systems before, it's always important for you to do more research. So go to these trustworthy websites, Circuit Digest, Texas Instruments. You can also check on IEEE. And also check on you can also check on IEEE. We usually have a lot of papers that have been written on this that you can easily follow. So if you check on IEEE, the Institute of Electrical and Electronics Engineers, you can easily, for example, right now, if I just click this, it's downloading a PDF. So you can easily find a lot of information on what it is that we have at the moment, and what it is that is expected for a modern design. Once you check out this, you're going to also see a couple of be able to do that. So you're going to check out a couple of electronic components. Like, for example, if you look at the board that Circuit Digest is speaking about here, they are speaking about this DW01A chip and this BB3A chip. So you can choose to do more research on this kind of chips that they are using here. So you can do more research on that. Just check out where you can find such a chip, and or how is it useful. So for example, if I check out this link, I can see that the DW01 chip is a battery protection IC. So this research is what enables you to create a good circuit without necessarily knowing knowing a lot of having a lot of information on such. So if you don't have prior knowledge, just with the topic that you want, the board that you're designing, do more research on it. Check out what has been done. There are a lot of websites that speak into this. There are a lot of papers that have been written by IEEE. Do more research, check out the kind of chips, check out the kind of circuits that like for example here we have a typical circuit using this chip. Just check this out. How have they done this, and how have they created this? Also, it's important for you to download. It's also important for you to download. This data sheet. So once you download the data sheet, downloading the data sheet is usually fast, very fast. Just Google search the name of the chip that you want to check out. Once you have that on Google, you can just pick any person, and you can just pick any trustworthy websites and download it from there. How do you know that the website is trustworthy? Most trustworthy websites usually have some sort of background information, and they usually explain a lot about what is happening and how you can be able to design your own. For example, this here is I've downloaded the datasheet for the DW01 chip. It's loading, just a few seconds. Yeah, so here we have it. We have general information, how we can use that, the kind of features that this chip can offer us. And if we're scrolling down, we can see this is how it looks like. So we had spoken about a symbol. So we can see this is how we can expect the symbol to look like. We also can check how its footprint should be able to look like. And also from this schematic, we can also see a typical application circuit that is offered in the datasheet. The datasheet is a list of requirements and or description of the component you want to use that has been offered by the of this. We are sure that whatever information we are seeing here is accurate. We're going to use this circuit to design our own. So this the DW01 chip. To use this chip, we can easily attach it to two MOSFETs, one resistor, one capacitor, and another resistor in order to make a basic circuit. So using the data sheet, it's important for you to really study the data sheet for any chip that you want to. Then from what the data sheet offers, you can easily be able to transfer that into your own circuit. So you don't really have to know much about the topic that you're going to do to design on, but it's important for you to do your own research. Do research, check the chips available. For example, we can also check the competitors to the DW101. For example, let me just check its alternatives. So we can see that there is another alternative here. So there is this AP9, blah, blah, blah. You can also just do more research on this, search this, see more details. And also another good way of search is using such blogs and exchange programs like Stack Overflow, Stack Exchange. We usually have a lot of guys that speak more on why you should choose this chip, and or people speaking about their experiences dealing with such chips. So someone can say, I've used this before, it's not really good because it fails after 2 weeks. So it's important for you to follow up, because if you're going to do a permanent design, you really won't want to create your own PCB and then 2 weeks later the client starts complaining, or your own project stops working. Then you'll have to redo the whole design. So just do your own due diligence, check out the online alternatives, check out what you have, check out on such exchange programs, check out what people are saying about such, and then you can make a more informed decision. You can see where people have made errors before. You can also use the data sheet. Always use the data sheet as your guideline, but it's also important to see how people have erred before. So once you do that, you can easily come up with your own circuit. So the schematic you're going to come up is going to look something like this. it's going to look like this. So, for example, here we have TP4056. This is a lithium ion charging management for us. We have a MOSFET that is going to switch on and off charging. So one with such a design, it's now easier. It's easier for you to translate this into a PCB. So not easier, but you really need to do this before you can create your own PCB. So do your own due diligence. Check out what you have online. Download data sheets. Out the schematics on the data sheets. Check out the forums on what people are speaking about as regards to that component, that particular component. Some component you really do not have to check. For example, passive components like capacitors, transistors, resistors, like capacitors, resistors, and there's no reason to check out what people are saying about them. But for most ICs, like this integrated circuit here, it's important for you to check out in order to use, because of a price perspective. Because, for example, if you're going to deal with PCB design, let me just check my favorite shop here, LCS. So if you're going to do PCB design on Okay, awesome. Hello. I hope everyone can still hear me. I'm sorry I took a 3-minute recess, a 3-second recess to take water. So if you're going to do PCB design, say you're going to create a lithium ion BMS system. So if you're going to search LCSE is a Chinese seller of components, usually sell such ICs very cheap. For example, if you can check out the prices here, they're like ridiculously low, like $0.001 for such components. So for example, let me just see this. So if you're going to create a charging IC, let me just let me select a suitable let me select a suitable topic here. Okay, yeah. So as you can see here, for example, this 114 chips that can be able to do battery management. So if I open this link, okay. Meanwhile, as most of you have KiCad on the way being downloaded. Yeah, I hope most of you are doing this. I hope most of you are downloading KiCad as we are speaking. And just on the final minutes of today's meeting, I'll go through a few basics of KiCad just to understand the interface and everything better. But and also a recap of what we've learned today. But okay, no problem. So you have the whole of tomorrow just to figure out how you're going to download that. For example, if I have selected the battery management ICs, so we saw that we have 5,000 ICs that offer battery management, and if you check here, we can see the price range from $0.05, which is about like 5 cents USD, 5 cents US dollars, and they're usually a lot in stock. So if you're going to see such a place, we have thousands of such ICs. Every IC has its own manufacturer. For example, this is from Shenzhen. We have its own part name. This is the FM2113. We have the FM4057. We have the DW02C. We were looking at the ago. I guess DW02C is is a newer version of the DW0A. So we have a lot of, okay, for example, this one is not recommended for new design. So it's also important for you to notice such kind of things. So this is not recommended for new design. Make sure you avoid this at all costs if it's it has such a label. But you see, we have thousands, literally tens of thousands of components. But how are we going to pick the right one for design? Keeping in mind a cost perspective, because for example, for this chip here, the FM4057, we can buy one piece for $0.2, yet we have another piece here that goes for around $0.05. So why should we pay more? Remember, the cost perspective gets significantly high once you consider that you're going to design components to be mass produced. This piece is rated in order to have 10,000 pieces of this. So you're going to need to buy this component 10,000 times. So it's really important for you to understand why you're going to select one component more than the other. Also, another important factor is if you design a board using such a component, say you design a board with this component, but they are not in stock, or the component fails, you need to redesign that. If say your boards are really required urgently, you need to redesign the whole board in order to use a component that is in stock, or a component that is not going to fail. So all these considerations have to be made before you forward with your schematic design. Check out the components, check out everything you have to offer. As I said earlier, this involves doing research online. Check out what is happening with some of these projects online, open source projects. If you've ever opened any device like a laptop, a computer, a motherboard, or any device, it's important for you to also note the kind of ICs they are using, so that you can be able to use such. So if you open a device made by Samsung, you're sure that most of the components they use have been sort of tested, and they're really sure that this won't fail after a couple of years. So you can choose to proceed forward with such components. So do your due diligence, check out the datasheet, check out the schematics, check out reviews online, and check out also the price for each component that you're considering, and availability, and whether it's recommended. Yeah, so it's really important to keep note of that. So once you're sure that your device has met all the categories, and in this, we're going to discuss more tomorrow, as we're going to speak more on how we're going to do this design. But in this component selection process, there are a lot of factors you have to consider: the kind of voltages you're working with, the temperatures you're working with, the technologies. Where is this device going to be applied? But the 10-day session we have with you guys is mostly focused on PCB. It's not really focused on circuit design, but I just wanted to capture a few basics here and there, so that we can be able to do this on our own. So I'm expecting tomorrow I'll have just a simple PCB, a simple schematic design. I'll go through it with you guys, tell you why I selected each component just for a few minutes, but we are not really going to dig deep into this, because we can lose a lot of time that we would have used in PCB design. So it's important for us to notice to select the right components. Once you select the right components, proceed with a very good detailed schematic design. Always use what the datasheet has to offer. Do not use what some random guy in Google Images has. So if you check out Google Images, you're going to see components, but do not select anything at random and decide. It's important for you to always check out what the datasheet says, and from the datasheet, with the design. Okay. Yeah, I think we've covered the basics. So just download the PCB download the P design software KiCad. It's important for us to also emphasize that KiCad is not software. It's a software design suite. It's a suite of multiple softwares with different functionalities. We're going to go through all of this and discuss more. If you're having troubles, please try to download this one. I don't know whether you can see it. The exe file. If you're on Windows, the one that is around 1.2 GB. If you're having issues downloading the zip file, try to download the one that is the exe file, the 1.2 GB file. I think that is going to work better. Yeah. So just download this. It's 1.2 GB. I'm assuming if you have a very good stable internet, it won't really take you a lot of time to download. So you can do that today, evening. Prefer you download that now. We prefer you download that now. Just have it download tomorrow and accessible. Awesome. So just a recap on what we covered today. Just a quick recap. Today we looked at PCB design. We looked at PCB design. Why we should avoid this for safety reasons, for security reasons. Why we should avoid working with such mumbo jumbo and cluttered things. The history of PCB design, how we didn't have PCB design in the 50s, 1950s. It was wires on posts with components around. How that changed to hand-designed PCBs. This is basically hand-drawn. It was more of an art rather than an engineering feat. So the best drawers usually were hired to draw this from an engineer's schematic. You are to draw this, make sure everything is not touching, make sure everything is straight as possible, and then how we switched over to SMT components. This year, through-hole components, SMT components, how SMT components has been able to minify electronic devices, how hobbyists like you, me, and or anyone else usually does their things, and why this is not really recommended for commercial purposes. This is good, but it's only good for your own thing, your own stuff at home. But once you want to proceed forward, it's going to be really difficult for you to do this in a more professional manner. From what hobbyists have to offer, you can easily create this on your own using just a cheap $5 soldering iron and copper board, like a plate board. The modern PCBs look like, how we can design that, and how we can have that manufactured. We have seen, we have also checked out just a quick process on how we can be able to order select components, how we can do component selection. We can delve deeper on that, but that's that. Your schematic with someone else, like a friend from the community. I can see there's someone, Nasser, if I'm pronouncing your name, I hope I'm not butchering your name, who's saying, kindly let us create a community. Let us create a community where we can share our progress. Yeah, that is awesome. So we can have a community, but yeah, so it's important for us to do reviews on each other's work. So you check, oh, is this good, is this bad, is this going to fail? Yeah. So once you've done your due diligence, created your own circuit, we can now export that circuit schematic and begin a PCB design. How we're going to cover, how we're going to place the components on board, how we're going to do the routing. So basically, how we're going to take these routes, these these routes, these copper connections, how we're going to make them, the thickness consideration, the design considerations, why we need to put a high-speed circuit here, why we need to have isolated circuits. For example, there are some circuits that you can't really put together because it's going to cause interference, and proper design, proper PCB design procedures. We're going to cover that. How we can be able to come up to move from a circuit design to a schematic design to here to a PCB design, and how we can be able to order that. That is what we're going to cover. So we have also checked out how the PCB is made, what constitutes a PCB, how a PCB looks like, why we need a PCB, the technologies used, any the kind of finishes. There are a lot of finishes. Please be aware that I've only covered the basics. Just check online. I can also share a couple of resources in order for you to understand like on a higher scale. But this is what we're going to focus on. So don't worry, we're going to focus mostly on this because this is more mastery into PCB design for the next few days. We're going to understand all of these technologies, why they are important, and how we can leverage that to make our designs better and more professional. Yeah, so we've got PCB design 6 and covered how we can be able to create a PCB from design stage, the schematic design, to ordering stage. We will be going through all of these steps slowly as we're going to design our PCB. So from tomorrow, I hope everyone should have downloaded KiCad, and then we'll begin with the design. We'll begin with design tomorrow. We'll have a simple basic schematic. We can do the design from there. And then by the end of the 10-day period, everyone should be able to come up with their own design, should be able to fix a problem that you're facing. Either there's a society problem and or your own personal problem. Say if you're lack of something in society, say these theft cases, you need to come up with a PCB with a design that can be able to take care of that, and or anything is encouraged as long as you're trying to solve a valid problem. Once we do the PCB design, and encourage everyone to also do their own, and then we can review that by the end of the 10-day period. And then I can also be able to show you how you can order your two GB, the KiCad 7.01. Then we will dig deep on that later. Awesome. Okay, so do I have any questions for me, or should I just proceed with a couple of comments and invite Jasin to comment also?